Here are 10 Python concepts that you really need to understand as fast as possible. First concept is dynamic typing. Now, Python is a dynamically typed programming language, and that means that whenever you define a variable, its type can actually change later on. So here we have a variable x equals 10. Because we've assigned 10, which is an integer, to x, the type of this variable is an int. However, later in the program, I can change this variable to something like a string, and there's absolutely no issue with that. This is one of the features of Python that makes it amazing, but also causes a lot of headaches. Let me show you what I mean. So check out this example. We have a very simple function where we add the values a and b, which come in as parameters. Now, even though we annotate these as an integer, which is valid in Python, you can define what the type should be, it's not actually enforced. What that means is that it's okay for us to execute this code and Python will run it no problem, but while we run it, we'll run into what's known as a runtime error. Let me show you what I mean. If I run this, you can see that we actually print out 30, which is the result of this first function call where we pass in two integers, and then we actually get an error where it says you can only concatenate string, not int, to string. That's because we passed a string and an integer, and again, because Python is a dynamically typed programming language, it will allow us to execute this code, but it will result in a runtime error. I'm showing this to you because this is one of the major downsides of using Python. This behavior can actually occur, and when it does occur, you'll get a runtime error, which can be difficult to debug and to solve. So when you're working in Python, make sure you're familiar with this type of behavior, and even if you add things like type hints or type annotations, understand that they're not enforced and that the code will actually be able to run, and you can get errors like this if you're not careful. That's why if you really want to make your code bulletproof, you need to check the types before you execute functions. So what I can do is paste in something like this, where I check if the type of A does not equal an integer. I can also do this for B, but in this case, if I save the code now and I run, you'll see that we get 30 and then we get invalid. So we no longer have this type error because we've not allowed the function to perform this operation that depends on both of these values being integers. So we'll dive into the next concept in just 1 second, but I quickly need to tell you about a fantastic resource I put together in collaboration with HubSpot, which is a free guide on how to land a developer role in the world of AI. Now, this draws on my over decade of experience and covers the top programming languages to master and the most effective methods for learning them. It includes the best practices for creating your portfolio and resume, along with recommendations for YouTube channels and other resources to enhance your development skills. I've left a link to it in the description, and you can check it out completely for free. Personally, my favorite part of this guide is the long list of resources like YouTube channels and websites that offer fantastic free ways to enhance your skills. This content is really focused on how to set yourself apart and distinguish yourself in this AI era, and offers essential insights to help you stay competitive as a developer. Like I said, this is completely free, and you can check it out from the link in the description from our video sponsor HubSpot, so a massive thank you to them. Now, the next important concept to understand is called mutability. Now, in Python, all of the types that we have are either mutable or immutable. Now, your standard types like int, float, boolean, string, these are immutable. That means that once you define them, they can't be changed later on. So if I do something like, string is equal to hello, I can't modify this string. Sure, I can make a new one, I can add something to it, but this is actually creating an entirely new string object. It's not modifying the existing string. This is the property of an immutable type. However, if we have mutable types, things like our lists, sets, dictionaries, or even a Python object that you define yourself, these are mutable. That means that you can modify them once they've been defined, and you can do things like append to them. And when I do something like append to my numbers, I'm not actually making a new list, I'm modifying this list and changing its contents. Now, it's important to understand this because when you use these types of objects that are mutable, you can have some unintended side effects if you're not aware. So look at this function here called mutation. We take in some list, and again, this is mutable. Now, inside of here, what we're doing is appending 10 to that list and then returning LST, which is the parameter that we have. Now, you might imagine that after this function is called, what's going to happen is we're going to make a copy of my numbers, and then we're going to have something like 1, 2, 3, 10 being returned from this function. Now, the question becomes, what happens to my numbers, the original list? Does this change or does this stay the same? Now, because we're working with mutable types here, when I run this, you'll notice that it does actually change. What happens when I pass something like a mutable type as a parameter to a function is we're not making what's known as a deep copy of this list object. we're simply passing a reference to this list. So when I make a change, something like lst.append, I'm not performing this change on a brand new list. I'm modifying the existing list that was passed in. So after this function is called, what happens is we return lst, which is really just a reference to this same list. And now we have these two things, the list after the call and my numbers being the same list with those mutations. Now, another tricky thing can happen here if you use a mutable value as a default parameter. So have a look at this. I have something called mutation. I have lst is equal to an empty list, and then I have lst.append 10. Now, what I'm going to do is I'm just going to call the mutation function, okay, 3 times, and then at the end, I'm going to print out the result of the 4th call to my mutation function. Now, if you've never seen this before, you might think that we're just going to get an empty list every single time, but watch what happens in the 4th call here. Okay, so I'm going to clear this and run, and notice that we actually get 4 10s inside of this list. Now, the reason for that is when I use a mutable default parameter, which is being used here, this is only created one time. It's not created every single time this function is called. So we're using the same mutable list over and over and over again for every single function call, which means by the time we get down to this 4th print statement, we now have the list that contains all of the modifications we made previously. So never use a mutable value for a default parameter. And if you want to do this, instead, you can say something like lst is equal to none, and you say if lst is equal to none, then lst is equal to a new list. So you actually define a new one every single call, and now you won't get that same behavior. And if you run this, you'll see that we simply get 10. Now, the next concept you need to understand is f-strings. Now, f-strings allow you to embed Python expressions directly inside of a string and make it a lot easier to print out dynamic content. Now, look here, you can see that I've simply put an f before some string. It can be a multi-line string, meaning you can have 3 quotation marks, or you can just have the standard double or single quotes. Now, when you place this f, whether it's lowercase or uppercase, it doesn't matter. It allows you to write any valid Python expression inside of a set of braces. So I can write something like the name or an age, and this will take whatever the value of this expression is, in this case it's just a variable, and embed it inside of the string. It will actually automatically convert anything that might not already be a string into a string for you. So in this case we have some int. Normally if we tried to add this int to a string we would get an error, but the f string is smart enough to be able to automatically convert this into a string. So I'll show you that this works just for our sanity here, and you can see that we print this out and everything is valid. Now if we remove the f, now we actually will not get that at all. So if I run my terminal here and we do this again, you see that I get the braces because it's not being interpreted as part of a kind of variable or an expression. Now we can do things like add, we can call functions. There's actually a lot of other things you can do with f strings, and I'll leave a video on screen right now that goes into a lot more details. Now, the next feature to go over is slicing. Now, slicing not only works on lists, it also works on strings and tuples, and is very useful when you want to grab different sections of an iterable object, or specifically a list string or tuple. Now, notice that I have a list here that goes from 0 to 5. Now, in other programming languages, if I wanted to grab a slice or a portion of this list, I would probably need to use a method, but Python has some fancy syntax that allows us to do this. So on my screen, we have 3 examples of how slicing works, so this might help you understand it, but let me break it down for you. A slice allows you to grab any elements between a start, an end, and a step, very similar to something like the range function in Python. Now, what you can do is you can define a start value, and if you do this, it defines what index you're going to start grabbing values from. So in this situation, we've started at 1, and that means that we're going to start at index 1, which has value 1, okay? Now, you also have the ability to define an end. You don't have to, which I'm going to show you in 1 second, but you can. Now, if you define an end, you're going to go to that index, but not include it. So in this case, we've decided we're going to end at index 4, which is element 4, but we're not going to include that in the output. So again, similar to the range function, we will go to the stop, but we will not include it. So that's why we've grabbed 1, 2, 3, 4. Now, we also have the option to include a step. Now, the step is how many elements we should skip over as we grab elements from this list. So if we look here, you can see that I have : 2. Now, what we've done is we've omitted the start, we've omitted the end, and we've included a step. Now, all of these values are optional, so you can decide what you want to include or not. But when we do : 2, that means we are going to start at the beginning of the list because we've not included it. So by default, we start at the beginning. We've not included the end, which means by default, we're going to go to the end and include it, which is important. But we've included the step value, which is 2, which means we're going to step over every first or every second index, So we're going to start at 0, we're going to step to 2. We're going to go to 2, we're going to step by 2, and we're going to grab 4. And then when we step by 2, we're outside of the bound of the list, so we no longer include any more elements. That's the start, end, and step. Now, as you've seen here, you don't need to include them all. So if you don't include the step, by default, you're going to be in the start end position. If you don't want to include the end, but you want to have a start and a step, you can write something like this. It's fine to have the 2 colons kind of combined together. Perfectly valid. And by the way, you can use negative indexing here as well. So if you look at this, we're actually doing : -1. Now what this means is start at the beginning, go to the end, but step by -1, which is really just a shorthand to reverse a list in Python. If you want to get crazy, you can start doing things like, go to -3. -3 means go to the third last element, but do not include it in the list. Okay, so -1 would be the last element, -2 is the second last element, -3 the third last element, so on and so forth. And you can get creative in how you use these with this slice syntax. The next feature that I want to go over is if __name __ is equal to __ main __. Now this is a common convention in Python, and a lot of beginners have no idea how it works, so I want to break it down for you. But before we write that code, I want to show you an example of why we need it. So to look here, we have a helpers.py file, and in this file, we want to call this greet function. Okay, whenever we run it, we just want to call this function. Then we have this main.py file, and this main.py file simply imports this helpers file. Okay, just imports that module. Now let's look at what happens when we run both of these scripts and independently. So if I run python helpers.py, of course it says hello from my module. But watch what happens when I run the main.py file. It also says hello from my module. Now the reason why it does that is because whenever we import Python code, we run the entire script that's inside of the imported module. So if we import helpers, anything that's inside of this file, we are going to run it. That's just how the import works, even if you're just importing a specific feature. So even if I do something like, from helpers, so let's go here, from helpers, import, and then I import the greet function, and I run main.py, you see it still says this. Okay, it's just a feature of Python. When you import code, you run the entire script. So why do we need this if __name equals __ main? Well, watch what happens. So now if I add this convention, and let's start by not printing out name, what you'll see now when I run python main.py is that it no longer prints out hello from my module. The reason for that is that this checks if this Python script is being executed directly. This condition here will only be equal to true if we directly ran this Python module. Now let me show you why that's the case, because if I print the name here, you'll see that when I run main.py, you'll see here that the name is equal to helpers, and that's because that's the module that we're inside of. Whereas if I run the helpers.py file, you'll see the name is equal to main. So whenever you run a script directly, the name variable in that script is going to be equal to __ main. But when it's imported from something else, it's going to be equal to whatever the name of the module, or in this case, the file is. So this check just simply tells us, are we directly executing this code? If we're not, then don't do this thing. And the reason for that, again, is because a lot of times we want to import and reuse Python code, but we may not want to actually trigger something to happen inside of that script. So I may have this script that does something really cool, and I might want to actually execute it directly, but then I may want to use 1 or 2 functions from it in another script. And if that's the case, I want to put this guard here so that I'm not executing something I don't mean to execute if I'm importing this from another script. Moving on, the next feature I have for you is a bit of a weird one, and this is the for else and actually while else syntax. So a lot of people don't know this, but you can actually tack on an else statement to the end of a for loop or to a while loop in Python. Now this else statement simply acts as a check if we didn't break out or we didn't find what we were looking for within a for loop. So I'm going to show you a really quick example here. We have numbers equal to 1, 2, 3. It's possible that we're going to search through this array or this list, and we're going to try to look for something, some kind of target, something like number equal to 5. Now, if we find it, we can print out, hey, we found it, and then we can break. And typically when we break out of a for loop, that indicates that our work is done and we've achieved whatever the goal is that we need. However, if we don't break out of this for loop and we exhaust all of the options, that typically means that we didn't find what we're looking for. And sometimes you want to handle that situation using something like an else statement. So that's exactly what this code is designed for. If I go here and I run Python main.py, you see it says 5 was not found. Whereas if I add 5 to my list, you'll see that it's going to print out found 5 and it doesn't execute this else statement. Now you might be asking, why do we need this? Well, it simply saves you adding a flag or a condition within your for loop. So let me show you what I mean. I can say found is equal to false. And if I find 5, I can say found is equal to true. And then rather having the else, I'm going to say if not found, then I need to print 5 was not found. So this is the alternative if you didn't use something like the for else. Sure, it's not a ton more code, but this is just kind of a better, cleaner way of handling this situation without needing to add that flag variable. Now, just like this works for for loops, it works for while loops as well. So it's perfectly valid to do something like while true, and then you can search for something. If a break occurs, then you're not going to enter the else. Otherwise, say, didn't find. Okay, so you can use an else with a while too, as well as with a for. And again, it's for the condition where you did not break out of the loop. The next concept to go over is star args and star kwargs. Now this allows you to accept an unlimited number of positional and keyword arguments. Oftentimes when you're writing a function, you don't know how many parameters you want to accept. Sure, you can make something like a default parameter, but if you want to accept something like an unlimited number of positional arguments or an unlimited number of keyword arguments, you can do that by using this convention right here. Whenever you add a star args, this actually means you'll accept any number of positional arguments, which are these right here. And if you add a star kwargs, this means you can accept any number of keyword arguments. And I'll show you an example of some built-in Python functions that use this, so it makes a bit more sense. Anyways, if I run the code, you can see that all of our positional arguments will be stored inside of a tuple, and all of our keyword arguments will be stored inside of a dictionary, and we can use them in the function as we please. Now, if you're looking for a practical example of this, look no further than the print function. The print function in Python can take any number of positional arguments, right? It can take something like a string, a few different numbers. It can take no arguments. It can take any number of them that we want. And if we look at print, notice what it uses. It uses the star args or star values. This just means it accepts any number of values and then prints them all separated by a space out to the console. There's all kinds of other functions in Python that use this star args and this star kwargs syntax, and it's very useful when you want to make your functions more dynamic and be able to accept really anything that you want. Obviously, be careful, don't overuse this, but in a lot of situations, if you want it to be very dynamic and accept any number of arguments, you use this. Moving on, we're talking about list comprehensions, which are quite unique and useful in Python. Now on my screen, I have a few different examples of them, and I'll run through them quickly because I have many videos on this topic. Now have a look here. What I can do is I can actually populate a list in place by writing something like this. I can say x squared for x in range 10. Now you need to have some kind of for loop structure. In this case, I'm just looping through the range 10. And then whatever I have on the left-hand side here is the expression that I want to evaluate for every single iteration of this for loop. Now what this does is it generates a list of squares for me, but we can get even more complex. Notice here that I've actually added an if statement. So I can now have some kind of condition, and I will only use this value x if this condition is true. So if x mod 2, so if it's even, is equal to true, then we're going to take x, and then you can see that we get all of our evens. Now we can do the same thing with a nested for loop structure. So I can say for sublist in nested, for item in sublist, and then I can take that item and I can grab or flatten a nested list by using this list comprehension. Same thing with something like the Cartesian product. I can actually take multiple values here, for x in range 3, for y in ABC. Okay, you get the idea. Now, the reason I'm showing this to you is because obviously it's useful, but this is actually significantly faster than writing code with a standard for loop. So if you just want to write out this same code, but you want to use a normal for loop structure where you're not doing it in place, it will actually be slower. The reason for that is Python uses a C implementation on the lower level for list comprehensions. So it's able to have less operations per cycle, which means that it can just perform faster. So if you actually look at these examples and you compare on very large numbers, if you're generating, huge lists, you'll see about a 20 to 25% speed increase by using list comprehensions. So it's definitely worth considering them, especially if you're making something that is more kind of performance dependent. So it's better to go with the fast approach rather than the arguably more readable approach by writing out the entire for loop. Moving on, we are talking about context managers, and I'm going to show you the very classic example, but it's an important concept to understand. Now, let's say we're working with a file in Python, and we have something like this, and believe it or not, this can happen. What we can do is we can open a file using this open function, and then we can write to the file. However, if you use this approach, you need to explicitly close the file. That's because if you don't close the file, then it's still going to be held in memory, and you can potentially have some memory leaks. So what would happen if an exception occurs before the file can be explicitly closed? Well, if that's the case, then we would have some kind of resource leak because we never closed the file and we're still storing that file handle. So I'm going to show you an approach that fixes this problem called context managers. I know this is a little bit of a trivial example, but the point is to demonstrate what a context manager is. So again, just keep in mind in this situation, I open a file, I write to the file, and then I need to close the file manually. And if something goes wrong before I'm able to execute this line, then that is potentially troublesome. Now, the context manager handles this for us. When we use with, which you've probably seen before, we can say with open as f. Now what happens is this context manager manages the context of this resource and automatically cleans it up as soon as we exit the context manager. Now, context manager, as it kind of describes, is handling what happens with a particular resource, and you'll see this very commonly if you're using things like databases or opening, again, files. So we open this file, and then what happens is in the background, based on how this is written, it will automatically perform any cleanup operations for us as soon as we exit this indented block. What that means is that even if we have an exception within this with block here or anywhere else in our program, it will automatically handle closing the file for us, so we don't need to worry about it, and it's just really the best practice. I have entire videos on my channel where I break down the context manager more in depth and actually write them myself, so you can look at the lower level implementation, but I wanted you to quickly understand this concept exists, and when you're using this with statement, what you're actually doing is you're working within a particular context that is controlled by this statement or the context manager, so it will automatically handle what you're doing with this particular resource, or at least closing it, opening it, all of the cleanup operations that need to happen behind the scenes. Now, the last thing that I want to show you here is something known as multiple assignment and unpacking. Now, this can actually go quite a bit further in Python. I'm just showing you a few quick examples here. So in Python, you can do something like this. You can say a, comma b, comma c is equal to something like 1, 2, 3. And as expected, we can have all of the appropriate values associated with whatever we defined here. Okay, so a1, b2, c3. But we can go a step further, and we can actually use this type of syntax to unpack iterable objects. So something like a list, a tuple, a string, anything that's iterable and that we can access values at index by, we can use this for. So I can actually decompose or unpack this tuple into its individual components, x, y, and z, by saying x, y, z is equal to something like my tuple. And now we get 10, 20, 30. And with this same syntax, we can actually perform inline variable swaps, and I can do something like a, comma b is equal to b, comma a, and now I've swapped the values of these two variables in line without having to manually create a temporary variable. Typically, if you want to perform a variable swap, what you would need to do yourself is you would need to say something like temp is equal to a. You would then say something like a is equal to b and b is equal to temp, because you're going to lose one of the values when you perform these assignments. But now we don't need to do that. We can do that in one line with this swap. Now, as I said, there's actually much more complex things I can do. So for example, I can do something like asterisk x, and then I can actually remove this and then have z. When I do asterisk x, this means collect all of the values up to, but not including z. So I'm going to grab 10, 20, and then 30 will be associated with z. There's a lot of things you can do using the asterisks. You can use underscores in place of variables if you don't care about what they are. So if we didn't want to access y, we could do x, comma, underscore, and then comma z. And again, I've made entire videos on my channel breaking down these concepts more in depth, but I want to leave it there just to give you a brief introduction. So with that said, if you guys enjoyed this video, make sure to leave a like, subscribe to the channel, and I will see you in the next one.